Okay, so this is my first attempt at filming myself doing a mark scheme, so I hope it's useful. This is the best I can manage with lighting and camera at home, I'm afraid. Hopefully you'll be able to see enough and zoom in if you need to, etc. I've posted the marked work back to Dr. Thompson to give to you with pretty detailed level of marking on it, much more detail than I would normally give, because normally I'd be seeing you to explain things. So hopefully a combination of this video and your marked work being returned will help to clear up any sort of misunderstandings, etc. So, solids under stress, this was the question booklet. So with question 1, it's a specified prac question. Obviously we used a slightly different method for ours, but we went through the method that WJC uses. Reading through the question stem, which of course you need to do, it tells us at the beginning that a long test wire and a reference wire of the same length and material are suspended from a common rigid support, which minimises the effect of temperature and the movement of the support. The support is not relevant to the temperature. The support is all about movement. The material being the same and the length being the same are what minimises the effect of temperature change. So explain how the effect of a temperature change in the wire is minimised. Here we would say the same length and material of wire means that any temperature change has the same effect on both wires. Okay, that's key there really. The rigid support wasn't given credit in the mark scheme because that's to do with minimising movement rather than temperature effect there. Okay, so question part 2. State what is meant by the elastic limit and explain how an experimenter would know whether or not the test wire has extended beyond its elastic limit. So the key thing here, of course, is the elastic limit is the point beyond which, I did credit people who said at which, I think that's fine, but just to be clear, beyond which is the official definition. So it's the point beyond which the wire or the material will not return to its original length. So that was one mark. The second mark then for how the experimenter would know is that if they remove the load or the force, and that was key. So you had to mention that you had to remove the force or remove the load, and then checking does it go back to original length or not. Okay, or it will not go back to its original length if it's past the elastic limit or something like that. You had to be quite precise with the next one, not just to say to minimise uncertainties, because that's in the question, so that wouldn't be credited, but state why a long wire is used rather than a short one. So greater accuracy in measurement because it will be a greater extension. Or you could say reduces the percentage uncertainty in the length, and that's because if you've got a greater length and a greater extension but a greater length, then you will have a smaller percentage uncertainty. The diameter being measured in several places. Lots of you talked about an average. Just use the word mean. Okay, we're at A level now. So accuracy of the cross-sectional area, or to obtain a mean diameter. You could say to check for uniformity as well, that would be okay. Right, we had our graph. Okay, so here's the results of the experiment. The original length of the wire is 2.40 metres and the mean value is 0.32 millimetres. So using the graph and measurements given, determine Young's modulus for the material of the wire. Appropriate number of significant figures as well. Okay, so the first mark is for working out the cross-sectional area of the wire. We're assuming it is a circular cross-section. So, key thing is, it's a diameter, so it's going to be pi times 0.16 times 10 to the minus 3 squared, okay, which should give you 8.04 times 10 to the minus 8 meters squared, or if you wanted to, 0.08 millimeters squared. I think we're about to have Shadow come and visit us. So that was your first mark there. Then you had to show that you'd taken two measurements from the graph. So I'm going to use the top point on the graph. So 28 newtons and 4.8 millimeters. Okay, so that's just showing that I've taken those. As long as those were clearly in your calculation, then you could still get the mark for it, but you had to clearly show what measurements you were using. Then we're using our equation for the Young modulus, so stress over strain, which we know is FL over AE, where E is the extension. So that becomes 28 newtons times the original length, which is 2.40 meters, over, I've just worked out the cross-sectional area as 8.04 times 10 to the minus 8 meters squared, and my extension is 4.8 times 10 to the minus 3 meters. Okay, stick all that in the calculator. I get 1.74 times 10 to the 11 pascals, or newtons per meter squared. There is a unit mark for that. Okay, no unit, no mark. So just be aware all the time. 1 mark for the calculation, 1 mark for the answer, but only if you gave it a unit. Okay. Calculate the energy stored then. So we're looking at when it's extended by 2.4 millimeters. So if I go back to the graph, grab myself a pencil and a ruler. 2.4 millimeter extension, so that's 3, so that's 2.4. Going up, going across. So I've got 14 newtons of load. Okay, so F equals 14 newtons, X equals 2.4 times 10 to the minus 3. So I'm just going to use the area under the graph, or Hooke's law, work is a half Fx. Well, it's not Hooke's law, but we know that it's obeying Hooke's law. And so that is going to be a half times 14 times 2.4 times 10 to the minus 3, which gives us 16.8 times 10 to the minus 3 joules. They would accept 17 times 10 to the minus 3 joules, or of course millijoules instead of times 10 to the minus 3 would be fine as well. Okay, right, moving on. So this was the trickier one, looking at the dislocations. Okay, so remember, a dislocation is where we have a missing row in our structure, in our crystal structure, which causes a weakness that can slip through the material. Okay, so the first thing I'm going to do is draw my two different rows of atoms. So I'm going to start with 6 in the top row, but you could do any number that suited you. So a few rows of 6, and then underneath a few rows with just 5, so we're missing an atom now. Okay, although there would be cross bonds through all of these, we're not particularly interested in the crossways ones. I'm just going to draw the long downwards bonds because they're the ones that are going to get affected by our dislocation. And I've done it wrong already, sorry. Okay, so that's rubbed out. Right, so our dislocation is occurring here, okay, and it's occurring because we have got forces acting in opposite directions, so we need to show those, or we need to clearly state that the forces are acting in opposite directions here. Okay, so what's happening is, because this forces are being pulled apart, okay, this bond here will break, and this bond here will be made, and that is how the dislocation will then slip across, okay, because gradually that will travel through the material. So we've got our force, we've got our bond breaking, we've got our new bond. Okay, so 4 marks, 1 for showing the dislocation, 1 for showing or explaining opposing forces. You could just explain that in words, that would be fine. 1 for showing the bond breaking, and 1 for showing the new bond creating. Okay, I know there's been some difficulty with some of these more wordy questions about dislocations and structure.